In this video, we're going to talk about ways to determine the area under a curve. So in this graph, we have f of x equals negative x squared plus 4x plus 5, and we want to find the area under the curve from when x equals 1 to when x equals 5, or excuse me, negative 1 to positive 5. So that means we're looking at this region here. Well, we don't have a set formula to do this, so what we could do is we could look at shapes that we know underneath and say, okay, I can get the area of this rectangle, and then I can keep getting more rectangles. And to get a more precise area, I would want to use even more rectangles as much as I could to get the most accurate area. And that's the idea of what we call Riemann sums. So in Riemann sums, we're using rectangles to approximate the area. And we can do it three different ways. We can use what's called a left Riemann sum, a right Riemann sum, or a mid Riemann sum. And what that refers to is what point of the rectangle is on the actual curve. In a left Riemann sum, the left corner of the rectangle is what is on the actual curve. And then our rectangles are going to be underneath to the right depending on the way the curve goes. Now on the left I only used 4 rectangles. On the right, in the yellow, I have lots and lots of little rectangles. So the more rectangles I use, the more accurate my area will be. For a right Riemann sum, the right corner is on the curve. So in this case I can see that these rectangles are all above the actual area, so this one is going to be an overestimate of my curve. In a midpoint Riemann sum, the midpoint of the top of the rectangle is what's on our curve. Again, still using those 4 rectangles, and if I used even more and kept making more midpoints, I'd get a closer and closer estimate. So again, just to help you summarize and see the difference, on a left endpoint is a left Riemann sum, the right endpoint is a right Riemann sum, and then the midpoint is the midpoint Riemann sum. So here I have the curve f of x equals x squared plus 1, and I made 10 rectangles. And I went through and calculated just to show you the difference in the actual estimations. So in a left Riemann sum, the area works out to be about 9.88. In a right Riemann sum, which we said we knew would be an overestimate, was 11.48. And a midpoint Riemann sum was 10.66. So they're all pretty close. The left is a little bit under, the right is a little bit over, midpoint somewhere in between. So here we want to practice calculating a right Riemann sum, finding the area between the curve f of x, which is x cubed minus 5x squared plus 6x plus 5, and the x-axis on the interval 0 to 4, and we're using 5 rectangles. So we need to split this whole region up into 5 pieces. So the way to figure out what the width of each rectangle is going to be is I take the difference in my interval and divide it by the number of rectangles I want. So this gives me the width of each rectangle, and that's going to be 4/5. So not to scale, but I'm going to have a rectangle at 4/5. I'm going to have one at 8/5. I'll have one at 12/5. I'll have one at 16/5. And then I'll have one that ends here at 4. Now when I draw these, because we're dealing with right Riemann sums, it tells me that the right part of my rectangle is there. So I can draw my rectangles in here, noticing that my right corner is on the curve. And I need to find the area of each of these 5 points. So I need to find f of 4/5. I need to find f of 8/5. I need to find f of 12/5. F of 16/5, and f of 4. Okay, so calculating each, plugging them in, f of 4/5 is 889 over 125, and I'm going to put those over here so we're going to have more room. F of 8/5 is 737 over 125. F of 12 over 5 is 553 over 125. F of 16/5 is 721 over 125. And f of 4 is equal to 13. So now I can find the area of each of these different rectangles. So to get my total area for each rectangle, I have to do 4/5 times its height. So the first one is 889 over 125. And then I'm adding 4/5 times the next height, 737 over 125. Plus 4/5 times 553 over 125. Plus 4/5 times 721 over 125. And plus 4/5 times 13. Now, because I have the 4/5 in every term, I could factor that out and then add all of my function values. Either way, when I add these all together and simplify, I end up with 724 over 25. So my area is approximately 28.96 square units. Now we can do the same thing, calculate the same area, but this time we're going to use left Riemann sums. So again, from last time we know that our width for each rectangle base has to be 4/5. Except we're going to start our first rectangle at 0 and go over to 4/5. So here, there's my 4/5 line. This is my first rectangle. Then I have my 8/5, my 12/5, 16/5, and my 4. So I can bring each line up, but I know it's the right side, the left side is where I want the point for my rectangle. So I still have 5 rectangles. This time we have slightly different values. So now if I plug in my f of 0, I know that that's 5. The rest of these endpoints are the same values we found when we were doing the right-hand Riemann sum. So this one is 889 over 125. F of 8/5 is still 737 over 125. F of 12/5 is 553 over 125. F of 16/5 is 721 over 125. And so now to get our area, again, we're finding the area of each of those rectangles. So again, in my first rectangle here, my base is 4/5, my height is 5. My second rectangle has a base of 4/5, but my height is 889 over 125. And I'm finding each of these areas and I'm adding them together. So then I have 4/5 times 737 over 125, plus 4/5 times 553 over 125, plus 4/5 times 771 over 125. And again, I could rewrite it and factor out the 4/5. I can also go to a calculator, plug this in. So my exact answer here when I add these all together is I get 564 over 25. Remember, we always simplify fractions. And just to get a better comparison, that is equal to about 22.56 square units. Now, in general, when we do these in calculus, the left-hand Riemann sum is the default. We always use a left-hand Riemann sum. Now just a little bit of notation, because we were adding up multiple rectangles, we can shorthand that using our summation notation. This is a sigma and it stands for sub. And what I'm doing to get the area under the curve is I'm summing the area of each of those rectangles, and that's what we just did in those last 2 slides. Now we'll be using this a lot more, especially in the next section when we start looking at definite integrals and the limits of those. So we want to make sure we know how to evaluate these. So this says evaluate the sum from n equals 0 to 5 of 2n. So this bottom is telling me the starting value, the top is telling me the end value. So I'm going to start by plugging in the 0, and I'm going to keep adding to that, but plugging in the next number up until I get to my top number. And I go all the way up to 5. So I plugged in 0, 1, 2, 3, 4, and 5 for all of those. And then I'm just evaluating. So I have 0 plus 2 plus 4 plus 6 plus 8 plus 10. And then I'm just adding 2 plus 4 is 6, 6 plus 6 is 12, 12 plus 8 is 20, 20 plus 10 is 30. And now some of these can get more complicated, and we do need to know their formulas. So again, just to see those, we have this list of summation rules. And so these we'll be coming back to, especially in our next section, which is definite integrals. The ones we probably use the most often are the summation of a single changing term and of k squared. Those are the two most common, but you do want to be aware of all of these.